The maximum likelihood estimation takes the following problem. Assume that you are given a parametric density, and I'm going to assume here that it's continuous, and I'm going to use a notation of a continuous density, but it does apply equally well if you have a probability mass function. And this density is parameterized by a parameter theta. And that theta we're going to assume is a d-dimensional real-valued vector. We're going to assume as well that we have access to capital N ID realizations according to that unknown distribution p theta. And the goal of maximum likelihood estimation is to come up with the theta that is best explained by the data that we have obtained. And the way we're going to do it is by forming what's called the likelihood of theta based on the data. Formally, the likelihood is defined as the probability according to theta of the set of points that you have generated. And here is going to take the form the product from I equal 1 to capital N of P of theta of xi, because I've assumed that my data is ideal. Very often, we don't work directly with a likelihood, we work with a log likelihood. The reason being a log transforms a product into a sum, and that's always much more enjoyable. And so the small L of theta is a log of capital L of theta, so it's a log likelihood. It becomes the sum from I equal 1 to N of the logarithm of the distribution p theta with an unknown theta of xi. And the maximum likelihood estimator, or MLE for short, is a quantity I call theta underscore ML for maximum likelihood. It's the argmax of this L of theta. And one thing I should write now immediately is that because log is a nicely continuous and increasing function, you can always argue that maximizing the likelihood is the same thing as doing the maximization of the log likelihood, small l of theta. And that's it. So the maximum likelihood is nice because there is a nice interpretation to it. It is the parameter that best explains the data. And second, it's also something nice because in practice, there are many situations where we can actually come up with closed form expressions. Now, the bad news is these situations where we have closed form expressions, they're a little bit artificial in that they correspond to the old view of statistics and probability where people were after closed form expression. In the context of machine learning, there's unfortunately many interesting situations where we don't have a closed form expression for what theta ML should be. But that being said, we'll get back to that later in this lecture to talk about algorithms that could allow you to estimate that maximum likelihood estimator fairly easily. So just to illustrate the point that sometimes there exists a closed form solution, it's useful to do a small exercise and derive what it is in simpler cases. And the example that we're going to use here is the following. Let us assume that you are given feature vector x and labels. So here, labels are real value. They're not necessarily taking values in a finite set, y, that are of the form theta transpose x plus some noise, where we know that the noise is modeled as a Gaussian random variable, which is zero mean and with variance sigma squared. And I'm going to assume that I'm in the setup where I can do maximum likelihood estimation with ID samples. And you're going to assume, I'm going to add that here, you're going to assume that you're given pairs xi, yi from I equal 1 to n, which are generated ID. So note here that I'm not really specifying the distribution that is required for generating x. The reason it doesn't matter is because the parameter theta that I'm trying to estimate is the one that allows me to relate y to x. And therefore, given x and y, I have all that I need to try to estimate theta. And strictly speaking, the distribution that I'm after, I'm trying to estimate, is the distribution which I could write p y given x parameterized by theta. That's what we're after. Okay, so when you have py given x, to evaluate it, you need a pair p pair xy, and will give you everything through that data set. So it doesn't matter what the distribution of x is going to be. Here the model is simple enough. It's additive. We have additive noise. It's Gaussian. The noise is Gaussian, so that you can actually hope to derive things explicitly. It's actually doable, so let's do that together as an example. Let me rewrite here explicitly the assumption that I'm making. I'm making the assumption that I'm given a data set that contains pairs of numbers yi, their features, their vectors xi from I equal 1 to n. I'm assuming that they're generated id. It's not critical here. And the model that I'm after is a model for p y given x parameterized by theta of y given x, that is saying that y is of the form theta transpose x plus some noise. So if you want to be a little bit more formal about this, it tells us actually what is the form that we have for py given x given theta. Indeed, if I assume here that this noise here is normal or Gaussian zero mean variance sigma square, usually normal is used for unit variance, then what it means is that what I'm looking for is a model of the form py given x parameterized by theta of y given x is telling me that I have a Gaussian distribution, 1 over square root of 2 pi times sigma exponential minus y minus theta transpose x squared divided by 2 sigma squared. This is what my model is according to what I've defined. And you see that if you know x and you know y, what I'm saying is that y minus theta transpose x is some Gaussian distributed random variable. It's important to note here that I'm assuming that sigma square is known. If sigma square were not known, we would have more work to do. But here sigma square is known, and all I'm trying to do is estimate theta. So let's go. Let's try to form the likelihood of the parameter theta that we're trying to estimate. The likelihood, by definition, is going to be this capital L of the parameter theta that I'm after, and it's the product from I equal 1 to n of these probabilities. So if I write things explicitly, it's the product from I equal 1 to n, 1 over square root of 2 pi times sigma exponential minus yi minus theta transpose xi squared divided by 2 sigma squared. And I hope that you see here the benefit of using the log likelihood. No one likes to actually work with products, especially if you then have to take derivatives. So it's much easier to transform that into a sum by taking the log. The reason we're allowed to do that is because we're going to try to maximize, and log is a monotonously increasing function over its domain. The log likelihood function is going to be small l of theta equal to the sum from I equal 1 to n of two terms. One of them is going to be minus the log of square root of 2 pi times sigma, and let me put parentheses to be very clear, minus the sum from I equal 1 to capital N. Oops, I already had that. Let me correct this real quick. Minus the log of the exponential is going to give you yi minus theta transpose xi squared divided by 2. When you look at this, it's not too hard to realize that this quantity square root of 2 pi sigma is actually independent of theta. So when it comes to trying to maximize the likelihood L of theta, I can discard that term because it's not going to influence my results. And therefore, note that the problem of finding the maximizer here is the problem of finding the argmax. Theta and L is by definition the argmax over all theta of L of theta is going to be exactly the same thing I'm doing the arg min, because I have a minus sign over here, over theta of the sum from I equal 1 to capital N of yi minus theta transpose xi squared. Okay, so again, this is just me rewriting what it means to compute the argmax using the fact that some terms in my likelihood have no impact on the result because they are constant and independent of theta. And it turns out that at that stage, we're in luck because expressions such as the sum of difference of squares or squares of difference are actually really nice to analyze, and we can do the computation absolutely explicitly. In general, however, remember that it's not going to be the case here. I want to show you how we can actually proceed to do that because it's a nice computation to know how to do. So let's go ahead and do it together. The first thing that I'm going to do is I'm going to rewrite this expression slightly differently. I'm going to think about this yi minus theta transpose xi as the components of a vector for which taking the sum from I equal 1 to n of the component squared is effectively taking the norm 2 squared. So I'm claiming here that I can rewrite that as the arg min over theta of the difference between a column vector y, which I will define in a second, minus a matrix x times column vector theta, norm 2 squared, where I have defined the following. Y is a column vector that contains y1 all the way up to yn. X is a matrix. X is a matrix whose rows contains the feature vectors. So X is a matrix of the form first row being x1 transpose. If I use a convention that it has to be a column vector, the last row is xn, transpose here. And theta is just theta as a column vector. And you can convince yourself that when I take the norm 2 squared, it is exactly the sum from I equal 1 to n of yi minus theta transpose xi squared. That expression here turns out to be quite nice to handle, in part because you can rewrite it slightly differently. I can rewrite that by definition as the following. I can say that it's the vector y minus x theta. It's a vector because y is a vector, x theta is a vector, transpose times y minus x theta. That's another consequence of the definition of the norm 2. And if I expand that further, you can realize that if you expand, you're going to get y transpose y, which is the norm of the vector y squared. There's going to be a cross term, and I'm going to get minus 2 y transpose x theta plus the last square, which takes the form theta transpose x theta. And now the goal is for us to find the theta that minimizes that expression. We have to be able to apply our usual approach when it comes to computing minimizers, which is to set the derivative equal to 0. What's tricky here is that we don't have a function of a single variable. We have a function of multiple variables in the form of the components of the vector theta. I don't expect you to be expert at functions of multiple variables and taking gradients and so on and so forth, but there are a few basic rules of calculus that are super useful just to make your life easier. And what you will realize is that when it comes to manipulating such expressions, it's not that different from the calculus that we're used to doing with functions of a single variable. The only reason we feel that functions of a single variable are much easier to analyze is because through, essentially 10 years at your level of brute forcing, you've tricked yourself into thinking that the rules are natural, but really they're not. You just learned them at some point. The same thing holds here for functions of multiple variables. So if you're not familiar with some of the calculations that I'm going to make, don't worry about it. Look it up either in my notes or on Wikipedia and train yourself to remember them. That's really pretty much all there is to it. So what I need to do here is I need to form the derivative of that norm 2 squared with respect to theta. So I'm going to write the derivative of the norm 2 squared of y minus x theta with respect to theta. Theta here is a vector. And you can convince yourself that the first term, y squared, in that expression, does not depend on theta, so the derivative has to be 0. For the second term, we're taking derivative with respect to theta, so we expect an answer that only depends on y transpose and x. The factor 2 should be there. The only trick when you do such calculation is that you have to make sure that the dimensions of the vectors you return actually make sense. And so in that specific case here, the answer is not minus 2 y transpose x. It turns out to be minus 2 x transpose y. And that's really because of the definition of what we mean by the derivative with respect to theta. It has to be a column vector. And finally, we need to take the derivative of that last term, theta transpose x theta. It really plays the role of a squared term. If you were to take the derivative of x squared with respect to x, you would obtain 2x. The same thing kind of holds here, but you have to be a little bit careful. And if you look up the rules of calculus for such forms, you would see that the derivative would be something of the form 2x transpose x plus times theta. Now, if you assume, for simplicity, that the matrix x transpose x is invertible, and very often that's going to be the case in practice, then you can observe that if you want to set that derivative to 0 with respect to theta, that's going to be equivalent, after a small manipulation, to saying that theta takes the form x transpose x minus 1 x transpose y. And so in that very specific case, we are able to actually compute in closed form what is the maximum likelihood estimator as a function of the data that we are provided. Here, the capital matrix X contains the feature vectors as rows. The vector Y contains the corresponding labels as rows. And we can compute explicitly theta. Unfortunately, in general, things are not quite that easy, and there's no chance that you can actually come up with a closed form expression. I encourage you to go through this small calculation. It's not fundamentally complicated, but you might need a refresher as to how to compute these gradients with respect to vectors here. And we'll see that again a little bit later in the class when we'll start talking about regression, and in particular, ridge regression.